Let's talk about radius of curvature of a parabolic path. Or this idea you can also extend to any other kind of path. But radius of curvature, and radius is normally associated with a circle. But then you are asked these kind of questions in examination when you have some different kind of paths. If the path is circular, then you can figure out the radius of that curvature very easily. But what if the path is not circular? For example, in this case, when a particle is projected with velocity 10 meter per second at an angle 60 degrees with the horizontal near the surface of the earth. So you also have this acceleration due to gravity. Let's say that is 10 meter per second square. So this is this kind of a situation in which the particle will have a parabolic path, and it has been projected with these parameters. So 10 meter per second, and this is 60 degrees. So you will have this velocity. When the particle was projected, you will have this velocity. This is the I cap direction, this is the j cap direction, and I hope my viewers know how to take components of a vector into perpendicular axis. So I have just taken the component of 10, and 10 cos 60 I cap, which will be 5, 10 sin 60 j cap, which will be 5 root 3. Okay, so that's fine, but then what is the question? The question asks you about the radius of curvature of the path. Notice, first thing, like the radius of curvature of the path is it's not constant, it's not a circle. So a circle will have a constant radius all the time, right? So here the radius of curvature might be changing. So when? So at the instant when the velocity vector of the particle becomes perpendicular to the initial velocity vector. Okay, so we have this initial velocity vector u, and when will the velocity of the particle get perpendicular to this u vector? So it should be somewhere here, right? Because at this point, at this instant, the particle will have a velocity which will be tangential to the path. And this is pretty interesting. Whatever your path is, the velocity is always going to be tangential to the path. So suppose if a particle is moving in this path, and here its velocity will be tangent to the path, right? It's pretty intuitive, and you can also prove it with simple mathematics. Why? So because if the particle have if the particle has a velocity which is not a component which is not perpendicular to the path, somewhere like towards this or this, then it will not stay on the path. Right? It's pretty intuitive that way, but you can think about the proof of this also. So at this instant, the particle is going in this direction, tangential to the path, and you can feel that if you if you extend this vector, if you move this vector here, u vector here, let's say this vector is v, if you move this vector v here, you feel like they are getting perpendicular. So you have an idea like when will the velocity get perpendicular. Okay, so also notice like you have to figure this out easily. If you have to figure this out easily, what is the velocity here? So the 5 I cap component is not going to change because the acceleration of the particle is in downward direction. So I cap velocity is going to be same. And when you dot product these two I cap components, you'll get a 25. So you only have this other component left from where you can create a dot product total u dot v to be 0, because they have to be perpendicular. So this is your v, right? So you can very simply say that this is minus 5 by root 3, because these I cap components are already giving you 25, so you need minus 25 from the j cap component, and that way you can very simply figure out the velocity when it is perpendicular to the initial velocity. So one thing has been sorted. Now we are thinking about the radius of curvature. Well, so let's first draw this velocity properly. This is the velocity we are talking about. It's tangential to the path. So at this point, if we can imagine this particle to be in a circular path, so what are the conditions? So if it's in a circular path, that circular path must pass through this point, right? And it should also have a tangent which is same as the tangent of the parabola. What do I mean by that? Okay, I will go into this, but first of all, let's do some this calculation. What is this angle theta? This will be very helpful. This is the tangential direction to the parabola. What is this angle theta? This you can figure out very easily. This length is going to be 5 by root 3 because of this j component, and this length is going to be 5. So you can figure out that theta, that tan theta will be 1 by root 3. This is a standard angle, 30 degrees, and from there you can calculate sine theta and cos theta also. Okay, but now let's come to this idea, this very important idea. So if you imagine the particle here to be in a circular path, that circular path must have this same tangent, and it must pass through this point also, right? So how many circles can do that? How many circles can have this common tangent to the parabola at this point? Well, the answer is not unique. You can have many such circles. 2 of them I draw here. So which circle to prefer? You see, these circles are becoming just like this parabolic path at this point. So you can model this particle going into this circle for some time, for an infinitesimal small time, but there are many options. So how can this radius of curvature be unique? We don't have any, I'm not aware of any mathematical technique, because mathematically I get only this. So when I was a kid, I used to get confused here. But then one thing we can do, you can use physics, because this is a question from your physics test, perhaps. So what can you do here? You can think about circular motion, some basics of circular motion, and let's first draw this normal here. So the center of these, whatever these circles, which could be one of our desired circle, would be on this normal, of course, because of tangent normal perpendicular property, and center of the circle lies on the normal. Well, that's okay, but let's not deviate from the path. This is also going to be your angle theta. Why? Because this you can do simple geometry. This angle is going to be 90 degree minus theta. You can think about these horizontal and vertical axis, and you can also think about this normal and tangential axis, and then you will see it very easily that that angle is going to be theta. But what we are trying to do here now is that this particle has an acceleration downwards, g, right? Because there is only one force acting on it, that is gravitational force, which will have a downward direction, and because of that there will be this acceleration on this particle which will be going downwards. Why are we going into acceleration? We are trying to do some modeling using physics. So what happens in a circular motion? In any circular motion, uniform or non-uniform, a particle always has a velocity which is tangential to the circle. I mean, this is not only true for circle, but this is true for all path. The velocity is always tangential to the path. But when you differentiate this velocity and figure out the acceleration in a circular motion, what do you get? You get these two components. One is minus omega square r cap. This is the centripetal acceleration, which is towards the center, and you also get a term alpha r t cap, a tangential acceleration. So this you can write also in terms of the speed of the particle, v square upon r cap, And then you can this is not that important here, you can just say that this is tangential acceleration, ATT cap. This derivation is very beautiful and very fundamental to circular motion, and if you have not seen it, you can go look for it in any textbook. And I would also like to make a video about this sometimes soon. So this tangential this radial acceleration, centripetal acceleration, which is towards the center, we can use that to figure out this r. So the acceleration of the particle is g downwards, so towards the center, whatever this circle is, the center will lie on this normal, right? So this angle is theta, so the centripetal acceleration of the particle is going to be g cos theta. And if we equate it to v square upon r, there is also this tangential acceleration. Don't worry about that, just think about this: g cos theta is equal to v square by r. V is the speed of the particle, and r gives you the radius of the circle. Pretty crazy. So this way you can figure out that desired circle, which you can say that is the uh, is the circle in which the particle can be seen to be moving for some instant. And now the calculation is pretty easy. You have this v here, you have this whole velocity vector, you need this speed only, so extract speed from there. You have g, you have cos theta, and you can solve it to get the answer, which will be 20 by 3 root 3. Thank you.